Before we charge off and perform a bunch of calculations here, let's get some estimates, or at least get some upper bound, lower bound information for the displacement that we seek. Remember, we want to get what the displacement is in the middle, whatever that maximum is somewhere in that middle span, and also ultimately we want to get the displacement out at the end. Right? And one way that we can go about making estimates is by not putting all of the load on there. Instead, for instance, get rid of the load that's out here on the outer edge and put only the load that's in the middle. That will cause the middle to sag more. It will cause then this piece out here that has no load on it to then just go along for the free ride. It has no flexural restraint to the rest of the system. It's just hanging out there, literally. Right? And so note, we can, from our mechanics and materials days, that's really just a simply supported beam with a uniformly distributed load. We know how to calculate or look up, in this case, what the maximum displacement is. It's 5WL to the 4th over 384 EI. L is the span between the supports here. And it's happening, of course, right smack dab in the middle. Right? We can also, with the same techniques, or using the beam superposition tables, we can come up with what that rotation is here at one of these supports. They'll be the same and opposite, of course, on either end. And from that, then, that rotation, we can use then this little right triangle that is formed to do rise over run. Remember, tangent of theta is about theta when theta is really small, which it will be in this case. And so then we can figure out that this rise equals the run times tangent of theta, or the angle itself. And so that would give us some estimate of those two values. Now, if they're upper bound, lower bound, well, let's look at what happens if we apply the rest of the load. Note that these two loads are counter to each other. Right? They cause different effects. One is trying to create smiley face, and then plus this little overhang that goes along with the free ride, whereas the cantilever load is going to cause frowny face throughout the whole system. So that means that what we've just discovered is clearly case 1 has given us an upper bound for the middle span displacement. It's not just an estimate now, it's definitely an upper bound. As well as we're going to find out that this expression here is going to give us the maximum possible that the end of the cantilever might rise up. Right? So when we're working with this one now, though, note what we can do here. This curvature that we've got for this beam, well, the whole thing curves all the way through, right? And so this middle span really just looks like a simply supported beam with an end moment, right? Just take that static equivalent load here and chop off it right to the right of the support, and you got the end moment, and you've got then, of course, the shear. The shear is going to go directly in the support and won't create this bending pattern that we have here. Right? And from this, we can go again look in the beam tables, or we can derive that the delta max in the middle in this case would be this m naught L squared over 9 times square root of 3 EI, right? And that really should be just square root of 3, not square root of 3 EI. And then you come over here, and the m is going to be given to us by WL prime squared over 2. L prime is the overhang length. So the total load out here is W times L prime. It effectively acts at the centroid, which is L prime over 2, hence where we're coming up with that moment value. And we can also either look up or calculate what that rotation will be. Here that is. And so that gives us the rotation, substitute in for the value of m from right above, and that gives us this expression here. Right? All of that, what that's going to give us is how much ultimately this tip goes down, because its connecting material also rotates. Right? So it rotates by this theta b up here, and then we got this little right triangle business here that gives us this drop, and then the rest of this is curvature of that overhang segment, which is just a little cantilever beam, W and L prime, which that little piece would be WL prime to the 4th over 8 EI. So the total displacement out at C would be the sum of those two, and that would give us a maximum value for how far down then the tip would go. And of course, in truth, if we really wanted to with this is all exact at this point. The reality will be the final delta C will be the sum of these two, one being up positive, the other being total net negative downwards. That would give us the actual delta C. Now over here though, the delta maxes do not occur at the same place for the two cases, so the reality will be the real delta max will be somewhere in between. We don't know where that's going to be. You could do a difference between these two that would only give you an approximation to the actual maximum in between, but it would be a useful number to have running around. Right, so there's a lot of wrinkles here about how we might go and actually perform the real calculation. This would be a beam superposition approach, and that's just fine. But if we're going to make sure that we've got that correct, then, in particularly since we only have an estimate for the delta max for this approach, now how do we go about doing the real calculation? And that'll be in succeeding parts.